Welcome to Physics of the Fidget Spinner. My name is Samantha Benelli. I'm the Physics and Engineering Specialist here at Ward's. And if everyone, it sounds pretty quiet now, but just remember to mute your phone so everyone can hear our presentation today. On the landline, you can press *6 to mute, and on the cell phone, there's just a little mute button where it's like a microphone with a line through it. So please mute yourself, but of course if you have a question you can unmute at any time. And if you also have a question, you can use our fancy little WebEx chat feature to type in your question as well. So let's get started. This kit, the Science of the Fidget Spinner, is broken up into two modules. We have an elementary and middle school level, and we have a high school level. So I was going to start with elementary and middle school today. Just to start you off, I want to let you know that both of the levels are aligned to NGSS standards. They are listed on the PowerPoint here. You can request that when we're all finished today by emailing our tech support team. I'm not going to go through and read every single NGSS standard to you that it's aligned, but just want to let you know that it is aligned and that information will be available to you at a later time when you want the PowerPoint. So the overview and objectives of the elementary fidget spinner kit. This kit is designed to help students learn about the effect of force on the motion of an object, as well as seeing the effect of mass on a rotating object. So I wrote here qualitative in nature, and that's because the elementary kit obviously doesn't dive into a whole lot of math concepts yet. This is going to be more observing the motion of the spinner and kind of thinking about the physics of what's happening. In this kit, students will determine the effect of force on the speed of the spinner. We're going to observe the mass of the spinning object and how it affects the force needed to start and stop it from spinning. We're going to feel the forces that a spinning object exerts as it's rotated. And we're going to experience the effect known as the wagon wheel, which feeds into the idea of persistence of vision. So some relevant vocabulary that the elementary and middle school kids are going to be learning with this exercise. First is force, a push or pull on an object, usually resulting in some kind of motion. Next is friction, the resistance to motion when one surface is sliding across another. Impulse, my favorite, I don't know why, it just is. A force acting on an object over a specified period of time. A force working on an object over a short period of time is said to have the highest impulse, whereas compared to the same force over a longer period of time with a small impulse. We're going to be talking about pivot, the central point, pin, or shaft which a mechanism turns, rotates, or oscillates. Tolerance, the amount of variation on an object that is allowable in order to still have the object function correctly. Last but not least, we're going to be talking about torque, the amount of force acting on an object that causes it to twist or rotate around a pivot point or axis. Just some background in general about fidget spinners and how they operate. This background information is the same in the elementary kit as well as the high school kit, so this content is the same across both. First, fidget spinners come in different styles, but at the core of them all are ball bearings, these little black pieces. The bearings allow the outer ring to rotate freely around the inner ring. And the quicker the force is applied, the faster the spinner will rotate. And once in motion, all fidget spinners eventually stop. No matter how good the bearings are, eventually friction comes in and eliminates the rotational energy and brings the spinner to a halt, eventually. So procedure number one, we're going to introduce force and motion. So the first part of the procedure is the kids are going to flick an arm of the spinner lightly and measure the time it takes for the fidget spinner to stop spinning. I did this earlier. I put some sample data in here so that we didn't have to wait the entire time for the fidget spinner to stop. So earlier mine was about 16 seconds when you flick it lightly. And this was probably about 12. I flicked it way later this time. So the students would record their data there. And then the second time, you'll want to flick it as hard as possible and then measure the time for the spinner to stop. So earlier, my hardest possible was 37 seconds. This one is probably going to be a little less than that because I have these fancy thumb holes in my jacket, so it just kind of hung up on my thumb hole there. So I did record the data for you there so that we didn't have to wait until the fidget spinner stopped. So then the students are asked, why did the light flick produce less time of spin, and why did the quick flick, why is that going to go way longer? And it's because we applied more force the second time. So it's going to be way more time before friction really has a chance to slow it down. So procedure number 2 in the elementary side is inertia. Yay! Again, I have no idea why I love inertia so much, but it's a pretty word, maybe. I don't know. So the second part is flick the spinner and measure it just regularly, not, I guess, your standard flick, if you want to call it that, not too softly, not too hard, just record that data. And I did that earlier at about 23 seconds, so it was my medium speed there. So the part with the inertia is kind of fun. I have silly putty. You don't have to use silly putty. I have it at my desk, so when I'm a fidgeter, so this is actually a perfect lab for me to do because I'm either doing this at my desk or I have silly putty in my hand and I'm just constantly using it. I am definitely, like, this was made for me. I know there's something else sometimes, but I'm definitely the ideal customer for these. So with the silly putty or clay or whatever malleable item you have in this similar nature, you'll want to break it up into 3. Silly putty is kind of hard because it stretches so much, but you'll want to break it up into 3 equal pieces. That one's a little small. Okay, and you'll want to roll them into a ball. And then we'll want to take the putty and insert it, not completely into the bearing hole, but just enough so that it's completely covered on both sides. I mean, you can put it all the way through, but I figure if you're using clay, silly putty's pretty good, but if you're using clay, it might get stuck in the crevices and that'll be messy. So you'll just want to make sure that everything is covered. So your bearings are completely covered on both sides. And then we're going to flick this. You'll have to remember to use the same amount of power to flick this one that you did last time. So that's why I say do your standard one. Don't try to make it harder or softer. Just try to flick it naturally so that you'll remember how to do it the second time as equally as possible. So the idea here is that, and I just touched it, so I'm not really showing you the exact idea, but the idea here is that with the silly putty covering the bearings, that displays inertia because the spinner is going to spin slower and it's going to stop faster than just the average flick. So if you wanted the spinner with the additional clay to spin for the same amount of time, what would you do differently? And that's when the students would say, well, in order to kind of combat the inertia that's happening, you'll flick it. I'm sorry, I just got in my own brain. You'll want to flick it slower so that it takes less time. Okay, we can go on. So I'll move on to the high school level of the kit. Again, it is aligned to the NGSS standards. If you're joining later, I just want to let you know that I said this earlier, but I'm not going to read all of the NGSS standards right now, but you can request the PowerPoint at the end by emailing our tech support team. So then all this information will be available to you later to read. So overview and objectives of the high school level. In this experiment, students will be investigating the angular velocity and the loss of energy of a fidget spinner. Now remember I said the elementary kit was more qualitative in nature. We're kind of taking the fidget spinner and thinking about what it's really doing. The high school version is more quantitative. So we're going to actually use a lot more math, calculations, and even graphing with this, and we're going to implement some technology. So the students will be determining the angular velocity of the spinner, as well as the energy loss due to friction, and we're going to be plotting an exponential decay curve. Super exciting stuff, I know. So the background is the same as the elementary, but I will repeat it for the people who have joined since I talked about that. So fidget spinners come in all different styles, but at the core of all of them are these black ball bearings here. The bearings allow the outer ring to rotate freely around the inner ring. The quicker the force is applied, the faster the spinner will rotate. And once in motion, all fidget spinners eventually stop. No matter how good the bearings are, no matter how good the installation, manufacturing, the friction will kick in and all of them will eventually stop spinning. So like I mentioned earlier, we're going to be implementing technology into the high school section. So as you can see here, I have a photo gate and timing system. I won't touch it too much because it's kind of set up nicely and I don't want to destroy it. But we have a photo gate set up here, and that's going to be collecting data for us. So the basic shape of most spinners is a 3-arm shape, and they can be used easily with a photo gate to quantify the way in which energy is lost. So our approach will be to measure the angular rotation rate of the fidget spinner using a photo gate. Then we're going to calculate the normalized energy of the spinner and fit the resulting curve with an exponential decay function and compare the results. Next slide, please. Thank you. So procedure number 1 for high school. We're going to be using a lab clamp to hold the fidget spinner so that it can freely spin. Now this took me a little bit to kind of master here. So when you set this up at home, the clamp isn't dead center of the middle. It's kind of slightly outward because that is the perfect spot where it rotates freely. So you'll just want to make sure. It might take a little fumbling in the lab before you can get started. So you'll want to position the photo gate so that the widest part of the fidget spinner arm interrupts the photo gate. So, and that's usually, if the spinner is like this, then the photo gate will want to be around it. You don't want to do it this way just because when it's this way, it's kind of way less, it's very narrow, but if you have it here, then there's a chance that the photo gate will collect the entire surface area and it'll be nice data. So that's why I have it set up this way. So the sensor will record the duration that the photo gate is blocked and calculate the angular rotation rate every second. So I did include sample data on your screen if you wanted to take a look at that. The ARB column, I don't know, it reminds me of Arby's. I don't know why it's called ARB, but the Arby's column will give the time the spinner arm was blocked. So I will talk a little bit more about that sample data on the next slide here. In the sample data set, the angular velocity is actually 4,839 degrees per second, not 4.8387. And that's because the millimeter width is converted to meters per second in the linear velocity calculation. So this means that the degrees are converted to kilo degrees per second. So that's how we get 4,839 degrees per second. So that actually sounds like a whole lot, but since there are 360 degrees per rotation, this actually corresponds to about 13 revolutions per second or so. So whoever did this really, I mean, that's pretty hard. I don't think I can achieve 13 revolutions per second, but the person who wrote this content is very strong. I'm not. So we can move on from the sample data now. So we'll go on to interpreting the data. So similar to kinetic energy, which is proportional to velocity squared, rotational kinetic energy is proportional to the angular velocity squared. So if we square the angular velocity, we can see how the energy changes. So there is some sample data there all flushed out, and all the buckets are filled with data. So the students will then plot their data points on a graph.
Someone wanting to know if they can see the spinner up close.
Oh, sure. The question is, can I see the spinner up close? So I do have a Ward Science fidget spinner here, which if you do buy our fidget spinner kit, then this beautiful spinner will be provided for you. And there we go. Check that out.
Thank you.
You are very welcome. Pretty sweet, huh? There you go.
Thank you.
You are welcome. Okay, let's move on to the exponential decay graphs. Yay! Okay. Now we're going to fit an equation to the points plotted on the graph. So energy decay very often follows an exponential curve, so we'll try that using the below equation, the one that's on the slide. So to determine the value of t, we can use any sample we want except 0, since that will give a nonsensical result. Obviously, that won't help us very much. Using a sample in the middle of the data collection works well, because that's when the photo gate is in its best data collection, and that's when the spinner's kind of reached its ideal point as well. So we always like to pick a nice middle value. So now we're going to calculate the energy percentage with our formula, the one that's listed above, using the value we calculated for t. And you're going to enter the result in the last row of the table that was on the previous slide. Then we're going to plot the values in the chart. And then this is when the students are asked, how well does the exponential function follow your data set? So the students, where was I? The students will answer this question, how well does the exponential function follow the data set? So that's when we'll see if the students are really close to that nice exponential curve. So there's some additional questions to consider in this experiment. Our study shows how energy is lost, and the students can ask, where does the lost energy go? Very good question. Question number 2, how do you think the mass of the spinner arms affect the value of t that we discussed on the previous slides? So if the spinner arms were heavier, lighter, would that make a difference, and why? And how would the value change if we perform this experiment in a vacuum chamber? We do have those. Well, we have a bell jar. That's kind of the same thing. How would the value change if we attach small streamers to the spinner arms? So not only is this spinning, but we have additional items hanging from the fidget spinner, so that I think that'll make a big difference. And how would the value change if we performed this experiment in space with 0 gravity? If I had the chance, I'd bring this bad boy up to space. I would. Can someone take me to space? Do any of you have access to space? Because I will gladly go to space and test this out. So if you have any questions, please email me. My email address is up there. And also, like I mentioned before, if you need a copy of the presentation, please email sciencehelp@vwr.com. That's our tech support team. They are fantastic. Also want to remind everybody that we have, including myself, a bunch of science people, scientists, former teachers at your disposal. Please email us anytime. We'd be very happy to help. On the following slide, I also have some product information for you if you're interested in buying the fidget spinner kit. So the science of the fidget spinner part number is below. Okay, this is your chance. Does anybody have any questions for me?
What else is included in the kit?
So the question was, what is included in the fidget spinner kit? So as I mentioned previously, we have a high school version and an elementary and middle school version. And these include enough materials for 5 classes. The fidget spinners, they come with these nice lab stands here. And they do not come with a photo gate though. The photo gate is available separately if you want one of ours or if you already have one. And you'll also need a stopwatch. I use my phone because you can just, I don't know, it's kind of easier than using a stopwatch if it's just me. And both of them come with a hefty packet of literature with questions, sample graphs, sample data, lots of background information that I didn't give you today because you would have been bored to death, but lots more than I gave you today are in those packets of information. So that's what's included in the kit. Thank you for the question.
We've got a couple questions here.
Okay.
If they don't have a photo gate, can they still do the lab, and how much is the kit and a photo gate?
So you can, I don't have list prices with me right now, but if you want to provide your information and email Science Help, our tech support team, I'd be happy to point you to your sales rep so that they can give you appropriate pricing. But if you don't have a photo gate, you can definitely do everything that I did previously before the photo gate option. You can also probably use a stopwatch. It would just be kind of difficult. But I would recommend a photo gate for all of the high school activities. But if you wanted to use this, like I said earlier, as more of a qualitative activity, then you can definitely do that without the photo gate.
You could film the spinner, put a mark on one of the arms to keep track. There are lots of video analysis programs you could use to get the time.
Great. Great. That's awesome. Any other questions? All right, guys. Well, have a fantastic afternoon, evening, wherever you may be. And thank you so much for coming. And we'll see you next time.